Welcome to the Deep Dive, your shortcut to being genuinely well-informed on today's most cutting-edge topics. Today, we're setting our sights on something, well, truly audacious, the space gold rush. We're talking about the monumental ambition of mining asteroids for their vast untapped resources. It's a concept that's rapidly moving from sci-fi to actual business plans. For this deep dive, we're digging into some heavy-hitting analysis and industry insights. Think titles like Space Gold Rush, Trillion-Dollar Asteroids, Asteroid Mining, The Next Frontier, and even Space Wealth Revolution, how asteroid mining could crash Earth's economy. Serious stuff. Our mission, to really unpack the incredible potential, the fascinating engineering challenges, the surprising economics, and yeah, the tricky ethical questions around this whole thing. Okay, let's unpack this. So to start us off, the idea of valuable asteroids isn't brand new, but the scale our sources talk about is just, wow. What actually makes these rocks so incredibly valuable?
Right. It's amazing. These aren't just, floating boulders. They're remnants from the very beginning of the solar system,
Yeah.
like cosmic time capsules. And because of that, they're packed with materials that are rare or hard to get here on Earth. We're talking platinum, gold, nickel, iron, rare earths, and, crucially, water.
Water. That one always surprises me.
It's huge. But yeah, their composition is key. It's pristine, concentrated stuff.
And the numbers. They're almost hard to comprehend. Our sources mention Asteroid 16 Psyche. The estimates for its metals, gold, nickel, iron, range from, $10 quintillion dollars up to maybe $700 quintillion dollars?
Yeah, it's almost meaningless. The number is so big. A quintillion is the one with 18 zeros.
Right. The thought experiment they mentioned, if you divided Psyche's value, everyone on Earth gets billions. It just highlights the sheer scale.
Exactly. And Psyche's just one example. You've got others like 511 Davida, 433 Eros,
Yeah.
adding up to trillions, even quintillions more. Even the Astrac database, tracking thousands of them, suggests mining just the top 10 near-Earth ones could net something like $1.5 trillion in profit.
Wow.
And NASA's estimate for the whole asteroid belt. Enough wealth for potentially $100 billion for every single person on Earth. It's staggering potential.
So beyond the big numbers, what specific resources are they really after? Why these particular materials?
Okay, so initially, the big draw is the platinum group, metals, PGMs. Platinum, palladium, rhodium, that group. Why? Because the concentration in some metallic asteroids is way higher than our best mines here, like 10 to 100 times richer.
100 times.
Yeah. And platinum, for instance, is vital for green hydrogen production. Big future market there. But then, as you mentioned, there's water. Some are calling it the new space gold rush.
Why water?
Because you can split it into hydrogen and oxygen. That's rocket fuel. That's life support. Right there in space. It'd completely change space logistics, make deep space travel much more feasible, less costly.
Okay. Fueling stations in space, basically.
Precisely. And then you have the basics. Iron, nickel, cobalt. Essential for building things in space. Actual space industrialization around the line.
Here's where it gets really interesting, though. Our sources indicate a shift. I always thought this was mainly about building stuff in space, using the resources there. But now, the focus seems to be on bringing precious metals back to Earth.
That's a really important point, yeah. There's been a strategic pivot. While using resources in situ, right there in space, is still a long-term goal, the immediate money, the clearer return on investment for these early companies, is in those high-value PGMs for the Earth market.
Because we already have established industries that need them.
Exactly. It's a known market. It helps justify the huge upfront costs and reduces the risk compared to trying to build a space construction market from scratch right now.
Makes sense. Secure the revenue first.
Okay, so that leads to the big question. How? Who are the companies actually trying to pull this off, and what's their plan?
Well, we saw the early pioneers, right? Planetary Resources, deep space industries, they had huge ambitions.
Yeah, I remember them. Big splash then. Not so much.
Exactly. They hit massive capital and technical hurdles, got acquired eventually. But they did crucial groundwork. And now we have newer players, like Astroforge. They seem to have a different approach.
Yes, Astroforge is a key one mentioned. Their model's interesting because they've apparently already secured contracts with refineries back on Earth. They're promising to deliver refined metals at current market prices. So they have a buyer before they even launch.
That sounds smart. A clear path to revenue.
It is. And their CTO, Hosea Keene, comes from SpaceX and NASA, worked on Falcon 9, Dragon.
Yeah.
So they have serious aerospace experience baked in.
Okay, so having that contract helps with funding, I assume. De-risks it for investors.
Significantly. It addresses the will anyone buy this question right up front. But, The technical challenges, the cost of actually doing it, those hurdles are still massive. It just makes the investment case stronger.
Right. So how do they even start? Finding the right rock seems like step one.
Absolutely. Prospecting is key. They use advanced spectroscopy, basically analyzing the light reflecting off the asteroid, often with small, dedicated satellites. Astroforge, for example, uses a two-step plan. First, a flyby for high-res pictures. Then a second mission actually docks and does detailed analysis on the surface to find the richest spots.
Docking with an asteroid
Yeah,
still sounds like science fiction.
it's happening. And they're initially targeting asteroids maybe around 400 meters across. Manageable size with current tech.
Okay, they find one, they dock. How do you mine in microgravity? You can't just send up a digger?
Huh. No, definitely not. Totally different environment. People are exploring ideas like literally giant bags to capture a small asteroid or harpoon and tether systems. Astroforge has this dual laser system. One laser melts the surface.
It melts the rock.
Melts the rock. Then a second laser basically acts like a little hammer, hitting the molten pool and making it splash upward.
And they catch the splash.
That's the idea. Catch the splash, collect the material. No heavy digging equipment needed.
Clever. And the refining? Do they bring the raw rock back?
Often, no. The plan is to refine it, right there, in space. Astroforge uses an all-electric refinery, solar-powered.
How do they separate the good stuff?
Magnets, mostly.
Yeah.
The PGMs aren't magnetic, but a lot of the asteroid rock, mostly iron, is. So you can use magnets to pull the iron stuff away, leaving the valuable non-magnetic metals behind. No complex chemicals needed.
So it's ISRU, in situ resource utilization, but for bringing stuff back, not just using it there.
Primarily, yes, for these early PGM missions. But the tech obviously helps develop ISRU for future space bases, too.
Okay, final step. Getting it home. That sounds like another huge challenge.
It is. Logistics are key. Companies are looking at reusable spacecraft, obviously, and advanced propulsion. Solar electric propulsion is a big one. Uses sunlight to power ion thrusters. It's slow, but incredibly fuel-efficient over long distances. Perfect for these long asteroid trips.
And how much are they bringing back per trip?
The aim for a single mission is about 1 metric ton of refined material. Think size of a mini fridge, maybe, with about 70% purity.
A ton. That's still a lot of platinum group metals.
It is. And they're aiming to do these missions for under $10 million each, which sounds like a lot, but it's actually a fraction of typical deep space mission costs.
Okay, this is all incredibly ambitious, groundbreaking stuff. But let's talk hurdles. What are the biggest roadblocks still standing in the way?
Well, the technology itself is still a major one. We just don't have the same level of geological understanding as we do for Earth mining. We're relying a lot on analyzing meteorites that have landed here and extrapolating.
So it's educated guesswork to some extent.
To a degree, yes. More like remote sensing and inference, which means the systems doing the sampling and extracting need to be incredibly smart and autonomous. They have to operate for months, millions of miles away, with significant communication delays. That requires really advanced AI and machine learning. Humans can't joystick this in real time.
Right, the time lag alone is a killer. Okay, what about the economics? We talked about the potential value, but what about the costs and market impact?
Huge question. The economic viability. First, the upfront costs are, well, astronomical, literally. Developing the tech, launching, operating, it's billions. Then there's the market risk. What happens if you suddenly dump tons of extra platinum or gold onto the market?
Prices could crash.
Exactly. There's a real risk of a supply glut. It could wipe out profits for the very companies doing the mining and potentially destabilize economies that rely on current mining outputs.
But I've also seen arguments, even from economists, that more supply could be good. Make these critical materials cheaper for new technologies.
That's the other side of the coin. Cheaper PGMs could boost things like fuel cells, green hydrogen, advanced electronics. It's a debate. There's that Goldman Sachs report saying the psychological barrier is high, but the actual financial and tech barriers are maybe lower than we think. Managing that supply influx carefully will be key.
Okay, beyond tech and money, what about the rules? Space law seems murky. Who owns this stuff?
Very murky. That's the legal and ethical issues bucket. The 1967 Outer Space Treaty is the bedrock. It says nations can't claim sovereignty over, say, the moon or an asteroid.
But it doesn't explicitly say companies can't extract resources.
Exactly. That's the ambiguity. So countries like the U.S. with the Commercial Space Launch Competitiveness Acts in 2015 and Luxembourg have passed national laws saying, yes, our companies can own the resources they extract.
But that's not international law.
Correct. We still lack a global consensus, which could lead to conflicts down the road. Though NASA took a big step in 2020, actually paying private companies tiny amounts for lunar samples just to establish the precedent of commercial extraction. And the Artemis Accords are trying to set some operational standards for peaceful cooperation.
And ethically. Is it okay to just go carve up asteroids?
That's a growing concern. Exploiting celestial bodies, ensuring the benefits don't just go to a few rich companies or countries, avoiding widening wealth gaps. Groups like the Hague International Space Resources Governance Working are trying to figure out fair, sustainable frameworks. Plus, companies need licenses like Astroforge, getting the first commercial deep space spectrum license from the FCC, and FAA approvals. It's complex.
Mining on Earth has huge environmental costs. What about in space? Is there an environmental impact we need to worry about?
It's different, but yes. The impact on Earth from asteroid mining itself is minimal, mostly just the rocket launches. In fact, the argument is it could reduce Earth's environmental burden
How so?
by potentially replacing some really damaging terrestrial mining for things like PGMs, avoiding deforestation, water pollution, carbon emissions from Earth mines. Returned materials would also be strictly decontaminated. NASA has protocols for that.
Okay, so potentially better for Earth's environment, but what about the space environment?
That's where the concerns lie. Could mining operations create more space debris? That's already a huge problem. And what about accidentally nudging an asteroid's orbit, even slightly? Could that create collision risks down the line? It raises big questions about space environmental stewardship. How do we manage this new frontier responsibly?
Are there other broader challenges? Political? Social?
Definitely. Geopolitics is one. Competition for these resources could easily lead to tensions, maybe even conflict between nations or blocks of nations backing their companies. And socially, there's public perception. Is this the best use of resources when we have problems on Earth? Safety concerns, ethical worries,
Right.
building public trust and ensuring benefits are shared will be crucial.
Okay, so huge challenges remain. But despite that, what's the timeline people are realistically looking at? When might this space wealth revolution actually happen?
Things seem to be accelerating. Right now, through about 2025, it's heavier in prospecting, tech development. NASA's Psyche mission launching soon is part of that. Then, maybe 2025 to 2030, we could see the first commercial extraction. Probably water from the moon first, as it's closer and vital for exploration.
And large-scale asteroid mining.
Projections point towards 2030 to 2040 for that to really start scaling up, along with the beginnings of actual in-space manufacturing using those materials. By 2040, 2050, space mining could be a major industry. You hear talk of the first trillionaire space miner potentially emerging in that time frame. And countries like China have very long-term plans, aiming for system-wide resource use by 2100.
Wow, that's transformative.
Yeah.
How does this change things fundamentally, both out there and back here?
It really enables this vision of an off-world economy. People like Jeff Bezos argue for moving heavy industry off Earth entirely, making our planet cleaner. You start seeing possibilities for space factories, fuel depots in orbit, building large structures in space using space resources. It unlocks deeper exploration, reduces the need to launch everything from Earth.
And the tech developed for this? Any benefits spilling over back to Earth? Spin-offs.
Absolutely. Technological leapfrogging. The extreme challenges, robotics, AI, autonomy, material science needed for asteroid mining, those breakthroughs, will almost certainly have powerful spin-offs. Think advancements in manufacturing, logistics, maybe even medicine, driven by the need to solve these incredibly hard problems in space.
So if we connect this to the bigger picture, what's the long-term view? Will space mining replace Earth mining?
The consensus seems to be probably not replace, but complement. Market analysts think maybe within 15-20 years, space could supply 5–10% of global PGMs. That's significant enough to impact prices and supply chains, but Earth mining will likely continue. It's more about fundamentally shifting our resource base, adding extraterrestrial sources into the mix, moving from scarcity to potential abundance, at least for some key materials.
This deep dive really highlights the sheer scale of it all, the incredible potential wealth, the amazing innovation needed, but also the very real hurdles and the profound questions it raises for us. It feels like we're standing at a crossroads, potential abundance, or maybe even chaos if we get it wrong.
It absolutely underscores the need for careful planning, foresight, strong regulations that can adapt, and genuine international cooperation are going to be critical to make sure this new frontier is developed responsibly and sustainably for everyone's benefit.
Absolutely. It really makes you think, doesn't it? What other unimaginable wealth might be waiting for us if we applied this kind of ingenuity not just to the stars, but maybe to challenges right here on Earth, or even within ourselves.